Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh to our respectful lecturer Encik Ahmad Hakimi bin Mano. Today in this video we will present about our project which is titled Basic Properties of Clay. Before we move to the next slide, I would like to introduce our group members. So, the first presenter is me, Nurhanis Arina binti Termizi. The second presenter is Yaka Arya Muhammad bin Sugio, and the lastly is Nur Ain Sufiana binti Yusuf. So let's move to the next slide, which is introduction. In this chapter, I will present about what is clay in generally and the objective for our project. So clay is finely grained rock or soil material that combine one or more clay mineral with possible trace of quartz, metal oxides and organic matters. Generally, clay has a lot of problems due to its low strength, high compressibility and high level of volumetric change. In geotechnical engineering, clay has been used and observed in numerous of geotechnical applications, and clay can be appear in various color from white to dull grey or brown to deep orange. So, objective. So, objective for our project is to study about basic properties of clay, which are particle size, hydraulic conduction, swelling, shrinkage behavior, shear strength behavior, physical and mechanical behavior of clay. There are 5 properties that will be discussed in literature review. So the last objective is to study about the methods to identify the clay. So the next is literature review that will be presented by me again. In this chapter, I will present those 5 properties that have been told in objective. So the first properties is particle size. Among the type of soil, clay has the smallest particles that can be only viewed by an electron microscope, and these small particles play an important part in clay smooth texture because the individual particles are too small to create a rough surface in the clay. So for the figure, and is compare the size between sand, silt and clay. So sand has the biggest particles, while clay has the smallest one, which is less than 0.002 millimeter. So the second property is hydraulic conduction. So hydraulic conduction of clay plays important role in emergence water problem, especially in impermeability, shear resistance, swelling, setting and swelling. Hydraulic conductivity is a property to express how water flow in the soil, which mean, in other words, to express the movement of water in the soil. So from table 2.1, it shows that hydraulic conductivity of soil, and clay has is the below one, which have the smallest value, which mean the movement of water in the clay is very slow than other soil. So the third one is swelling shrinkage behavior of clay. Swelling is effective in reducing the strength of in the slope and foundation bearing capacity. Swelling occurs when the infiltration pressure is greater than pressure from covering or structure. However, swelling pressure is depend on type of clay, mineral, soil structure, cation exchange capacity, pH, cementation, and organic matters. So from graph 2.1, it shows that the graph of typical task of a consolidation test by odometer. So the first one is shear strength behavior of clay. Shear strength behavior of clay is fluent the bearing strength of clay, slope stability of clay, and bearing wall of the basis of clay. When clay subjected to shear, the volume change in the drainage stress, which make clay does not allow the water to escape from the pores, which is create the excess water pressure. In order to determine shear strength of clay, it can be performed by direct shear test. Triaxial compression test, vein test, and standard penetration test. From graph 2.2, it shows the graph of typical test for shear strength test by triaxial compression test. So lastly is physical and mechanical behavior of clay. Consistency limits define the relationship between ground particles and water and the state of soil relative to varying water content. When the moisture content keep increasing, clay change its form. It form from solid to semi-solid, semi-solid to plastic state, and plastic state to liquid state. So we can look the detail the flow from graph 2.3 that show the relationship between water content and the volume of the soil. So that's all from me. I will pass the next slide for the next presenter. Thank you.
So now is 3.0 methodology and 4.0 result. 3. Layer structure and content. Sample preparation. Samples included both terrestrial clays and marine clays. 2-layered clay mineral, kyanite, and 3-layered mineral were used as standard samples for quartz as primary minerals. So all samples were prepared by using water-Nevis method. And X-ray diffraction. Geiger flex ray to see with a monochromator was used under standard test conditions. Differential thermal analysis DTA, which is the differential thermal analysis, and also DT, which is the thermal gravity, were simultaneously conducted using model TGTA 220. 15 milligram sample was filled in a platinum cell and temperature was reached about 10 degrees Celsius per minute. Alpha alumina as reference material and measurements were taken in an azotic hemisphere. The peak surface was calculated by using Simpson's method. And then is ignition loss method. So a clay sample of approximately 19, which is the size is smaller than 2, containing non-organic matter was weighed in a 5 milliliter magnetic crucible and placed in a desiccator at 55% relative humidity for about 4 days. Samples were tried in a muffle furnace at 100 degrees Celsius for 24 hours after measuring initial weight. Loss of weight was determined after cooling the samples into room temperature. So this procedure is repeated after drying the sample at 530 and also 800 degrees Celsius for about 24 hours. At least 3 samples are used in each measurement. So this is the layer content, this is the result. So select samples. An endothermic peak occurred at 100 degrees Celsius and again at around 650 until 800 degrees Celsius in the 3-layered sample. In the 2-layered sample, however, endothermic and exothermic peaks occurred at 546 degrees Celsius and 197 degrees Celsius respectively. So the changes in weight in both samples occurred at the corresponding temperature of endothermic peaks due to the loss of absorptive water and the desorption of structural OR, which is the diagram at the side, which is the right one. So this is the diagram that shows the result. So this is the artificially mixed sample, so DTA method. The amounts of structural water 4.57 and 13.12 is in monazite and corallinite, respectively, estimated from DTA were largely similar to theoretical values and were calculated using structural formula of clay minerals. So, and a strong positive correlation between the endothermic peak and area and weight reduction was observed in both 3-layered samples and 2-layered samples. So next is the muffled furnace method, which is the heating temperature. In the 3-layered sample, a considerable amount of interlayer water was lost at H2 degrees Celsius, which is this one, and then 200 degrees Celsius. The loss of crystallization water occurred between 700 and 850 degrees Celsius, and a sufficient degree of dehydration occurred at 800 degrees Celsius. In kaolinite, however, only 3 temperatures around 540 degrees Celsius were selected for heating, as peak endothermic temperature was about 546 degrees Celsius. Reduction in weight of kaolinite was 12.06 degrees Celsius, 12.09 degrees Celsius, and also 12.42 degrees Celsius. Percent following 6 hours of heating at 530 and also 550 degrees Celsius. If this rate of dehydration had continued, the reduction in weight following 24 hours of heating may have been between 13.4 and 13.7 percent, rather than a theoretical value of 13.9%. Okay, so second is the sample weight. The loss of interlayer water at 100 degrees Celsius increased as sample weight increased, but the loss of structural OH at 530 and 800 degrees Celsius tended to decrease. Okay, this is diagram at the side. A comparison of values for moisture loss in DTA and PG indicated that the loss of moisture was consistent when weight of the sample was around 19. Since the area is likely to become large if the weight of the sample is too small, the optimum weight for analysis was set at 19. And then is the heating duration. The rate of dehydration increased within a short period and reached a plateau within 6 to 12 hours, which is the diagram at the side as well, which is at the bottom right. In light of this, a heating period of 24 hours was considered appropriate. So the next one, which is the applicability of ignition loss method. Okay, a positive relationship between the amount of water lost upon heating and the amount of clay mineral in the mixture was found, which is the diagram below. The estimated values of clay mineral content in different mixtures, which is table below as well, closely corresponded with actual values, thereby indicating the applicability of the muffled furnace method. So the diagram above, which is the relationship between moisture content and content of clay minerals, and while the below table is that is the estimated values of clay mineral content for the standard samples. Okay, and then which is the local samples, the identification of clay minerals. Prior to using the ignition loss method, clay mineral in local samples were examined by X-ray diffraction, which is the DTA and DG. So, which is the differential thermal analysis and also thermal gravity. Application of ignition loss method. The results from the ignition loss method were largely similar to those obtained by X-ray diffraction, which is the A and DG table is below. A few differences between the result from DTA. Okay, refer to the table below. So the next one, which is 3.2, which is the plasticity. Accessories include a digital display 0.01 mm resolution for displacement measurement, interchangeable cylinders containing an internal spring of 50 Newton per centimeter, force determination, a control spring, and a cylinder cone with a 30 mm base and an angle of 30 degree. So this is the specs, the components that exist in the test. The plasticity is directly given by the intention force measured on digital display. No cracks or any kind of plastic flow, and the test is considered valid. And the force value displayed on the penetrometer device is actually the plasticity value. Samples prepared by 30-minute milling of 700 of each raw material in porcelain jar eccentric mill. Ceramic suspension obtained was dried in an infrared oven. Granules integrate and sieved through a 500 mesh sieve. Dry powder was added to water, adjusting a water content of approximately 25 water content. Paste was homogenized in the mechanical stir. Okay, so this is the diagram above. As you can see at the right one, which is the clear indentation, which is the left one, which is showing a lack of water, and the right one, which is an excess of water. So it just show two different kind of situations that involving different type of different kind of plasticity. And then this is the result. Okay, P presented low plasticity compared to F. R possesses a larger quantity of clay minerals and lower quantity of non-plastic materials and impurities when compared with E. So here we go to the last one, which is the 3.3 hydraulic conductivity. So material, commercial electric and bentonite clays are prepared by excavating a shell deposit, air drying and fragmenting the broken shell, controlled kiln drying and grinding the product to the desired fragment size. Elite, approximately 50% elite and 25 calamite, with same chloride, quartz, feldspar, and a little calcite. Bentonite clay contains 80% of sodium morillite with some interlaid smectites, chlorides, and elite quartz and feldspar. The reference buffer material RBM is compacted bentonite mixture of sand bentonite and consists of sand and Saskatchewan bentonite mixed with the required amount of water to produce a water content of 16 to 18%. A dry density of 1.67 megagram per meter cube, and a degree of saturation of about 85%. Sand is a crushed, medium, subangular, well-graded, and silica sand. Hydraulic and mechanical properties of the material are dominated by the clay fraction. Next is the test equipment. Aim of the test was to use lower gradients than had been used before in such low permeability clay. Specimen diameters range from 32 to 95 mm, and sample heights range from 5 to 60 mm. To limit the effect of aggressive pore fluid diffusion of water through the walls of the supply lines to the atmosphere, after the specimen had been compacted into its cell, the load transfer ramp was installed and the reaction plate tightened into position without adding axial stress. Maximum effective stress was the swelling pressure generated by the specimen as a result of its compacted density and access to water. Zero displacement cells means that the effect of consolidation process pressures and pressure gradients caused by hydraulic gradients have been eliminated or reduced. Once the specimen had been compacted into test cell, its average particle arrangement was fixed. Result can be expected to reflect principally the relationship between hydraulic conductivity and hydraulic gradient. The pressures experienced by the specimens were self-generated. Effective swelling pressures in very rigid zero displacement cells. Water pressures at the top and bottom porous plates were externally applied and controlled. Fluid reservoirs above and below the specimens were positioned to give constant head and therefore constant gradient conditions. So this is the picture or diagram of the test equipment. Okay, and these are the components. So the next step is flow measuring system consisted of an all-water interface in a high-pressure thin bore glass tubing. Gauge has a resolution of 0.005 mm and could be used up at pressures up to 10 megapascal. Operation with the glass tube particle led to changes in hydraulic gradient between 1 and 6 depending on the specimen length. Gradient less than 50, the gauges were used with the tube horizontal. Separate flow gauges were installed in the inflow and outflow lines to monitor any possible leakage. Permeameter cells were tested for leakage before and after each test. And this is the result of hydraulic conductivity elites. Diagram below shows results from a dense elite specimen compacted to 2.03 megagram per meter cube and tested with 0.5 megapascal back pressure. The one straight line relationship are in the plot of log versus log indicates constant hydraulic conductivity and direction flow. The test started with a gradient of 1.8. Two things are evident from this figure. Measured flow and outflow rates were similar, indicating that hydraulic conditions were stable and similar flow rates and hydraulic conductivities were measured. And the last one, which is the benzenites. The benzenite and sand benzenite specimen were tested with either deionized or saline pore fluid. Initial saturations ran from over dry to over 90%. Of the 49 benzoate and sand bentonite specimens tested, 33 of the specimens with higher density. Examples are shown in diagram at the side for an initial clay density of 1.09 megagram per meter cube and saline pore fluid. Linear behavior with constant hydraulic conductivity K is equal to 1.2 times with 10 until 11 meter per second was observed in this specimen for gradients from 12.5 to 400. The remaining 6 specimens with lower densities exhibited transitional behavior into separate torsion segments. The gradient side shows data from 3 constant gradient tests lasting up to 440 days on bentonite. There is some scatter in the data but no consistent pattern of change in hydraulic conductivity with less duration. And then the specimen can be assumed to have reached hydraulic equilibrium.
Assalamualaikum and very good afternoon. My name is Nur Ain Sufiana binti Yusof and I am going to explain about conclusion and recommendation for this project. Conclusion. In conclusion, clay was very important in engineering industry. The study of its property was very important in order to make sure that clay can be used more systematically according to industry requirements. Previous research that has been carried out study on clay properties and behavior based on proper and laboratory results through several experiments. Objective that to study basic properties of clay, which are particle size, hydraulic conduction, has been achieved. The experiment including to test the clay's behavior in layer structure and content, plasticity, pore size distribution, surface tension and contact values, and hydraulic conductivity. Experiments carried out with care, preparation and procedure, and the test and the result then summed and analyzed. Recommendation. In future, there must be high consumed construction material in use of clay in many industries regarding clay use. New application or practice in clay use must be upgraded in future use. For example, to make clay is best used in future is to make sure that clay have high resistance to fire. The clay must be added by materials such as organic compost, pine bark, compost leaves, and gypsum to improve its structure and help eliminate drainage and compaction problems. That's all from me. Thank you.